So in this video, I'd like to discuss the vibrations of a block of wood that's floating on water. So we'll assume that we have basically a surface of the water. We have a block of wood. So here is the block of wood. And here is the water. So here's it floating. I'll assume that, so this is the wood. I'll assume that the top area of the wood has an area of A. We'll assume that the mass of the wood is given by M. So M is the mass of the wood, so M. And A is the surface area, the top surface area. And the idea is that we'll assume that this block of wood is floating on water and that it's oscillating up and down. It's floating up and down. And this, I'd like to know exactly what the oscillation frequency is for that piece of wood. So I'm going to make an assumption that if I look at the side view of this, here's the box, here's the wood, side view, and I'm going to assume that the wood is floating and portion of the wood is underwater, portion is above the water, and I'll take that point marker, that point where it's where the line, where the surface of the water hits the wood. We'll just put a little dash on it. Assume that if it moves up, right, then I'll call X, right, to be displacement up from equilibrium. So the equilibrium point when this equilibrium, can't even spell equilibrium properly. So that point, right, where we reach equilibrium is the point that I'm going to keep track of. And so that displacement, right, where it's above the surface of the water is going to be called X. So let's do some calculations and calculate what it is. I'm going to assume that there's no dissipation. So this model assumes no dissipation. Yeah. No energy loss, which is not realistic, but let's just assume it's no energy loss. Okay, so how would we do it? So we have the mass of the object. So we know that the sum of all forces using Newtonian mechanics, right? And I'm going to assume up is positive. So I should say up is positive. Is mass times acceleration, which is second derivative dt squared, is equal to the sum of forces acting. Well, we know that the force of gravity is there, but at equilibrium we don't have to worry about it. So the net effect is if the object moves up by x, then we expect that the force is pulling down with a minus the, so if this is x, the volume of material, right, that has been removed, right, is actually area times x, minus x actually, but so this is the volume of material, right, that would represent, that's not, that would be the volume of water, right, that's not being displaced by this material if it goes up. And we expect that the force, right, of this general, the mass of material of the density water, the density of water times the volume gives me the mass of the material, that this volume is now no longer displacing, they're no longer displacing. So this mass times G is the force that's actually pulling this material. So there's a force of gravity pulling down, but there's a volume of material, right, that no longer is being pushed up by water. And so, but that volume is actually acting downwards, so this is actually rho ax times g. And so we have a differential equation already, right, that tells us something about the, well, this is the our Archimedes principle, right, of displaced water. So this is just the equation. So with this in mind, right, I can move everything to one side. And so we get a second order differential equation, dt squared plus the density of water times the area times g over the mass, and is equal to 0 times x equal to 0. But we know the general equation, right, that we want to look at, right, is d squared for vibrations without damping, but generally any damping, including damping, would be the general equation plus gamma of dx dt. So this is the damping factor, which is 0 in this case. We don't have damping. And omega O squared x equals 0. So this is the equation that we already know solutions of, and we have a video for that, so if you want to double check for the mass spring system. So now to find omega squared is equal to the density of water times the area of that plank of wood times gravity divisible by mass. And so omega O is equal to the square root of the density of water times the area times gravity times the mass of the object. And of course omega, right, if we had to put omega we also know is 2 pi over t. So this is also equal to 2 pi over t. We can solve for t, and so we get t is equal to 2 pi, and flip everything around, m over density of water times the area times gravity. So this is the time period of the oscillation, and this is the angular frequency. So this is the angular frequency, and this is the time period. Pretty straightforward, nothing special. So the main ideas you get out of this is we construct differential equations, and we compare them to equations we already know. So we have a damping factor of 0. There is no damping. But if we did have to include damping, right, we know that the general formula, right, well, there is a general solution for that equation, but we'd look at 3 different cases. So this specific case, right, is actually considered as underdamping. But remember, there's three types of general dissipation problems that in this equation. There is critical damping, overdamping, and underdamping, and you should review that in your in the video that's on mass spring systems that goes over the solutions for this. It's also in the lecture notes.